Welcome to the debate.
Good to be here.
Today, we are opening up the blueprints of innovation. We're looking at that critical, often messy phase where a vague idea either solidifies into a product or, well, dissolves into chaos. We are dissecting Chapter 7 from the book Complex Product Development Model, or CPDM, written by Christer Sandahl out of Lund, Sweden.
In this chapter, Capture, Staffing, and Requirements, it sounds so dry on paper, but Sandahl, he manages to elevate it to something almost philosophical. He claims right at the start that requirements constitute the soul of a product.
It's a powerful assertion. He writes, if you specify your product right, you get it good. If you specify the right product, you get it sold.
And that's the hook. But the debate today, I think, is about the how. The methodology Sandahl lays out is just incredibly rigorous. It's hierarchical. It follows this very strict outside-in philosophy, where you have to map the entire environment before you even think about the product.
Exactly. And my stance is that this rigor isn't optional. This structured refinement, separating the what from the how, is really the only way to manage modern complexity. If you don't do this, you don't get the product the stakeholders asked for. You get what I call the accidental product, something built on, the whims of the moment rather than the soul of the intent.
Look, I see the value in structure, I really do, but I come at it from a slightly different perspective. When I look at the examples in this chapter, the endless tables, the wait state machines, the unique identifiers for every tiny detail, I start to worry about overkill. It feels like we're building this wall of bureaucracy between a user's actual needs and the engineer's hands.
I see why you'd think that, but let me offer a different perspective. That wall is actually a foundation. Requirements are the ultimate security. They are the only way to secure verification. If you cannot trace a feature back to a stakeholder requirement, it probably shouldn't exist. You must start with the environment restriction requirements. You have to know the laws, the physical limitations, the environment, before you can even define the black box.
But Sandahl himself admits that requirements are often considered boring, hopeless to understand, and impossible to update. He knows this is the part of the job that, well, everyone hates, and yet he prescribes a method that seems to double down on all that density.
Because the alternative is the engineer guru.
I knew you were going to bring up the guru.
It's a central point in the text. If requirements aren't precise, that decision-making power, it just slides down the hierarchy. It lands with the strongest technical personality, the engineer guru, and then suddenly the product isn't solving the user's problem anymore. It's solving the guru's desire to use a specific tech stack or, try out some new coding trick. The requirements protect the product from the engineer's ego.
Well, that's a bit of a cynical view of engineers. I tend to think innovation happens when you let smart people play within the boundaries, not when you micromanage them with a spreadsheet.
But you need the boundaries first. Let's look at the house example in the text to see what I mean. This is the first core example Sandahl uses to explain environment restriction requirements.
Right? The house.
So look at Table 7.5. Sandahl lists items like Swedish Environmental Code, 7th Chapter, or Malmö Urban Planning.
Sure, legal constraints.
But notice how they're categorized. These are environment restriction requirements, ER. You can't design a house and then check if it fits the urban plan. These are fixed constraints. They are the box you must live in.
I agree that you can't break the law, but does listing Swedish environmental code in a requirements table actually help the engineer? It feels like we're just stating the obvious.
It helps because of the refinement process. This is the outside-in magic. If you look at Table 7.9, which shows the house black box compound requirements, you see how those high-level restrictions refine into actual design goals.
Okay, give me a concrete example from the table.
Take the restriction regarding cooking and dining. That's a high-level concept, but in the table, it refines into specific requirements. The lake shall be as visible as possible, AR 11.1, or the dining space shall support up to 8 guests, AR 6.2. You go from a vague environmental constraint to a testable requirement.
Okay, I'm looking at that table, and I have to challenge you on testable. Look at AR 6.1. The atmosphere during dining shall be relaxed.
It's a valid requirement.
It's a vibe. How do you verify relaxed? You can verify 8 guests by counting chairs. You can't verify relaxed with a ruler. If I'm an engineer, and you give me a spec that says, make it relaxed, I'm going to roll my eyes.
And that reaction is exactly why the CPDM method is so necessary. Relaxed is the stakeholder's wish. It's the top nesting level. The process Sandal describes involves taking that wish and refining it. Eventually, relax translates into, acoustic damping requirements, specific lighting lumens, spatial dimensions, but you must capture the soul, the wish, first. If you skip writing down relaxed because it's vague, the engineer might just build a cafeteria-style room because it's efficient.
So the vague requirement acts as a kind of placeholder for future precision?
It acts as a compass. It ensures the efficiency of the engineer doesn't override the intent of the owner.
I can accept that for a house. We all understand dining rooms. But let's move to the multiplication toy example. This is where the methodology gets very, very technical and where I start to see cracks in the one-size-fits-all approach.
The multiplication toy is where the distinction between restriction and behavior becomes critical.
But why does that distinction matter so much? I mean, in the end, the toy has to work. Why do we need separate tables and distinct taxonomies for restrictions versus behaviors?
Because they are verified differently, and they impact the design differently. Let's look at Table 725. This is the requirement set for the toy. You have a restriction requirement, R111. The toy shall be child-proof.
Right? Static, it just sits there and doesn't hurt the kid.
Exactly. Now, compare that to a behavior requirement like ARB-8.4. The toy calculates and shows the product value. That is dynamic. It involves a stimulus, pressing a button, and a response.
Okay, but Sandel spends a lot of time in this section discussing the hardwired versus microcontroller variants.
He does, and that's the genius of it.
To me, it felt like he was blurring the lines. He talks about how a hardwired circuit solves the problem differently than a microcontroller.
No. He's proving that the black box requirements remain identical regardless of the solution. That is the point. Whether you use a mess of logic gates, so the hardwired version, or a sleek chip, the microcontroller, the requirement, ARB-8.4, calculates and shows value, does not change. The soul of the product is technology agnostic.
Ah, I see what you're saying. You're saying the requirements protect the product definition from the supply chain.
Precisely. If you write your requirements based on a specific chip and that chip goes end of life, your product definition is broken. If you use the CPDM method, your requirements stand firm. You just swap out the white box implementation.
That's a fair point on modularity, but I want to talk about the cost of this rigor, because when we get to the calculator example, specifically the calc logic environment, I feel like we're stepping into over-designed territory.
I disagree. The calculator example is where the rigor prevents the most common software failures.
But look at figure 7-18 through 7-23. We are looking at wait state machines. Sandel is mapping out states like wait for trail opt 1 digit.
It's a precise map of interaction.
It's a pocket calculator. Do we really need a complex diagram showing the transition between waiting for a digit and waiting for an operator? It feels like programming. It feels like I'm writing a state machine in C++, but I'm being forced to do it in a diagram first.
But you're missing the distinction. This is the design-free specification. You aren't defining variables or memory addresses. You are defining the external behavior.
But Sandal introduces stimuli history in table 736. He says we need to remember that the user pressed specific buttons previously.
Yes, because the reaction depends on the history.
But he insists we do this without defining internal variables. That is mental gymnastics. If I have to remember that I pressed 5, then plus, I'm essentially defining a variable in memory. Why pretend otherwise?
Because once you define a variable, you are designing the white box. You are telling the engineer how to store it. Is it a stack? Is it an array? The requirement shouldn't care. Stimuli history just says the device must act based on the fact that these buttons were pressed. It leaves the implementation to the developer.
It just sounds like a distinction without a difference to me.
It is the difference between success and crashing. Look at figure 728. It maps the conclusion normal use case. By forcing the specifier to map out every stimulus at every wait state, you catch the divide by zero error.
The classic edge case.
If you just tell a developer, build a calculator, they write the happy path, number, operator, number, equals. They might forget that the divisor could be 0, but the wait state diagram forces you to draw a line for every input. You physically have to draw the line for 0 when waiting for the divisor. It forces you to define the error behavior before a single line of code is written.
So it forces you to face the unhappy path.
Exactly. It forces you to define how the soul of the product handles failure.
I can see the argument for a calculator where precision is everything, but what about the phone book example? This is the one that really stuck with me as potentially excessive.
The phone book example illustrates restriction requirements for data structures. It's vital for scalability.
It illustrates micromanagement. I want to look at table 754. There is a restriction listed. Max comp per book equals 128.
A clear, quantifiable restriction.
But why 128? Why are we putting a hard limit of 128 contacts in the requirements document? That feels like an implementation detail. Maybe the engineer only has a certain amount of RAM. Why lock that into the soul of the product?
It's not an implementation detail. It's a business decision for the roadmap. Sandal talks about roadmaps in chapter 730. By setting max cont per book to 128, you are defining the scope of version 1.
But if I'm the user, I don't care about your roadmap. I want to store 200 friends.
And that is exactly why it must be a requirement. If you don't write down 128, the stakeholder assumes infinite. The engineer assumes whatever fits in memory. Then, when the user adds the 129th friend, the app crashes or slows to a crawl. By stating 128, you align expectations. You can plan to move to an SQL database in version 2 to handle thousands, but for version 1, the restriction is explicit.
Implicit versus explicit. I get it, but look at the volume of documentation this creates. Table 7-55 is the phone book behavior. Table 7-57 is interface stimuli. Figure 7-39 maps out append contact to phone book.
A crucial scenario.
It's the save button. You type a name, you hit save. Do we really need a formal scenario diagram for file incompletely written exception use case?
I would argue that is the most important diagram in the entire chapter.
Why?
Because what happens when the disk is full? What happens if the battery dies while saving?
Usually the OS handles it, or the app just crashes.
The app just crashes. That is the failure of requirements. That is spaghetti code. By defining the append contact scenario explicitly, as Sandal shows in Figure 7-39, you force the team to discuss file writing failures. You mention the file incompletely written exception. Developers always forget that. They write code for success. The CPDM method forces you to design for the moment things go wrong.
I admit, fixing a bug in the design phase is cheaper than fixing it in the field.
It's exponentially cheaper.
But I still struggle with the time investment. Sandow briefly mentions that for high-stakes products, like a nuclear plant, which he alludes to, this rigor is non-negotiable, and I agree there. But for a phone book app, if I spend 6 months writing tables and defining wait states, my competitor has already launched.
Or your competitor has launched a buggy app that loses people's data, and you launch the robust one that captures the market.
Speed is life in the software world.
But quality is longevity. And remember, the outside-in approach allows for speed later. Once you have defined the black box interfaces, the inputs, the outputs, the restrictions, you can iterate on the inside rapidly. You can swap that file system for a database without breaking the user experience. You go slow now to go fast later.
Go slow to go fast. The classic engineering paradox.
It is.
Okay, I will concede one major point to you. The distinction between restriction and behavior.
I thought you might.
When Sandow talks about restrictions being static, like must run on Windows or must be childproof, and behaviors being dynamic, must calculate sum, it brings a lot of clarity. I've seen so many teams mix these up. They try to write test cases for restrictions as if they were behaviors, or they forget to verify the restrictions entirely until the very end.
Exactly. They built a whole product and then realize, oh, it was supposed to be waterproof.
Right, and by then, it's too late. The house example in Table 7.5 really drove that home for me. You can't paint the walls and then realize the zoning laws don't allow a second floor.
You really can't.
So I see the value of the tables as a contract. It's boring, it's tedious, but it forces alignment.
It ensures that we are all building the same thing. The engineer guru can't hijack the project because the table says no. The stakeholder can't complain about the feature set because the table says, this is what you signed off on.
It depersonalizes the conflict. It makes the table the authority, not the manager.
That's a great way to put it. The requirement is the authority. The requirement is the soul.
I suppose my hesitation still comes from the fear of losing the human touch. We focus so much on the logical structures, the wait states, the stimuli history. I worry that if we stare at Table 736 too long, we forget that a human being has to actually enjoy using this calculator.
That's an interesting point, though I would frame it differently. A product that crashes isn't enjoyable. A product that divides by zero and gives you a nonsense answer isn't human, it's broken. The rigor ensures reliability, and reliability is the foundation of a good user experience.
I can't argue with reliability.
So, do we have a verdict?
I think we have a convergence. I'm still skeptical about doing this level of work for every product. I might skip the weight state diagram for a prototype, but for a production product, you cannot let engineers design the product before the stakeholders have defined what it is. The black box must remain closed until the requirements are set.
I'm glad we agree on that. If you start soldering wires or writing classes before you know what the weight state implies, you aren't engineering, you're just guessing.
And guessing is expensive.
The CPDM method, refining from the outside environment in, using those rigorous tables we've been discussing, is a heavy lift. It is demanding, but it ensures the soul of the product survives the development process.
And for those who want to see just how deep this goes, looking at the actual tables in the book is a real eye-opener. The complexity of the hardwired versus microcontroller breakdown alone is worth the price of admission.
It certainly is. For our listeners who want to dive into those tables, the book Complex Product Development Model, CPDM, is available in both hard copy and ebook formats.
It's a dense read, but if you want to understand the engine room of product development, it's all there.
Thank you for joining us on this deep dive.
Thanks for having me.